this is just a quick video that will kind of generally look at a few different important parameters in the case of a pretty well-behaved data set from suburban Maryland. So this is actually the Maryland example from the paper that does have very strong phenology that we do not want to be dealing with if we're just looking for disturbance. So in this case, if you recall from the paper, it was looking at the land cover change from mostly from forest or agriculture to impervious surface. So fairly easy to characterize, but important changes in the watershed. And so right now I've started with the demo dataset user configuration file because that's what you'd likely be starting with as well. I've directed myself towards the appropriate my working folder, and I've gone ahead and already loaded up my HOCO, my Howard County points. So many of these are disturbances for which we know roughly what year that happened. So I'll show you the metadata here. So we've got most of these are like forest to impervious, forest to residential, and there's also a few stable forest and agriculture just to make sure we're getting a picture of the what's happening across this scene. So we'll just look at the first 9 here. And you can see it's pretty crazy, right? Because this is looking at all of the data. So if you see something like forest to impervious, forest to residential, you're not really able to tell what's going on very well because this includes all days of year. So a lot of this noise is from phenology. So when you've got a nice data set that's, a nice data set in that it is pretty densely filled with data, then you are able to go back and severely restrict the DOY ranges that you want to look at. So in our area, day of year 150 to 260 is roughly summer. Maybe I'll make a couple other changes here. I'm gonna go with NDVI for right now. NBR or NDVI, probably both fine for our purposes. We'll exclude any really low values of NDVI. Probably 0 to 1 would be fine as well. Some of these I'm not going to worry about right now. A penalty of 3, that's fine for now. Again, remember that all of these parameters have a nice tooltip, and as well as more information in the Google Doc instructions. Filter dist, we're gonna keep that at 3. So 3 will be better than 7, for example, to probably to accurately date disturbances, because we're not kind of averaging the error of the fits over more points. This is averaging them over fewer points, gives you more precision, but difficulty in sparsely populated data sets. PCT, for the moment, I'm gonna even drop that down lower just to give you an idea of what that's going to do, where that's going to fit our trajectory in the data. And these other ones we'll leave for now and maybe come back to in a little bit. So we'll say okay. Give this a new name. And let's see what changed. So the main thing you notice is we've gotten rid of a lot of the phenological noise, and probably already doing a little bit better job of fitting some of these curves. So we are in the part of the data set that is the most difficult to fit, because most of these early ones, so 1 through 9, are some of the early year disturbances. So you can see there's pretty minimal data pre-disturbance, for example, here, number 5. So these ones are a little bit challenging, but I'm sure we can do a bit better than we're seeing right now. Note that these fits are kind of just going up through the middle of the data, so near the median fit, and that's governed by that PCT. So that percentile fit is sort of where this line is going to float in the data. For NBR, that's probably fine. For NDVI, you generally want to raise that number up so that you can float more on in the higher percentiles of the data where you're not fitting atmospheric noise as much. So let's go back and change that for starters. We double it. Just change that one thing. So you can see that made a big difference in terms of the fit. You can see we're floating up towards the top. We're avoiding some of this downwardly biased noise. You can see we have a nice fits in these early disturbances. Well, this one doesn't get it all the way down to the bottom, but still kind of captures the rough dates of the disturbance. We'll make one more change here. We'll force the complexity to be a little bit higher, which again is okay for this application since we're really just looking for the date of the largest disturbance. See if that got us anything. So yeah, that helped. You can see this one, is modeled better than it was before. This does allow us to really capture these early disturbances quite well at this point. Let's look at one more set just for fun. See how we did when things get a little bit easier in some cases, and we're picking up these disturbances relatively well. So of course you could either do that. You could also do the parameter optimization, and there's another video for that, or just mess with these parameters a little bit more, but I think we're most of the way there, and this is basically the parameter set that we used effectively in the paper.